The remediation narrative is an accounting error. It is a line item carried forward on a ledger that no one intends to close. The Hanford Site, occupying 580 square miles of semi-arid plateau in southeastern Washington state, is not undergoing cleanup in any operational sense of that word. It is undergoing observation. The distinction is not semantic. It is structural. It is encoded in the budget allocations, in the engineering timelines, and in the half-lives of the isotopes migrating below the surface at this exact moment. This migration operates at a rate determined entirely by geology and physics. It is completely indifferent to federal appropriations or contractor milestones. The Central Plateau tank farms hold 56 million gallons of high-level radioactive and chemically hazardous liquid waste distributed across 177 underground storage vaults. That is the inventory. That is the core fact from which every other calculation in this audit derives. The 149 single-shell tanks that constitute the oldest portion of that inventory were engineered beginning in 1943 under Manhattan Project construction protocols. Those protocols specified a design service life of 20 years. 20 years was the operational assumption. The engineers who drafted those specifications wrote them, knowing that the post-war period would produce permanent disposal solutions. They believed the tanks were transitional infrastructure. They assumed that 56 million gallons of waste chemically aggressive enough to dissolve mild steel would not remain in mild steel-lined concrete cylinders indefinitely. That assumption failed. The transitional infrastructure became permanent infrastructure by default, not by design. Those tanks are now operating in their 83rd year of service. That is 4 times beyond their certified lifespan. There is currently no credible full transfer timeline established for the majority of their contents. The concrete shells have been exposed to thermal cycling, chemical attack, and the continuous radiation flux of their own contents for over 8 decades. The rebar has corroded. The concrete has cracked. The liner welds have failed. The question is not whether the single-shell tanks are failing. The question is at what rate and toward what receiving environment. The double-shell tanks, 28 of them constructed between 1968 and 1986, represent the upgraded generation of that storage architecture. They were engineered with an inner and outer steel shell separated by an annular monitoring space. This design was intended to provide secondary containment and leak detection. Their design life was also finite. Several are now approaching or exceeding 40 years of service. They hold high-level waste inventories that generate continuous internal heat loads and chemical degradation of the steel. The annular space monitoring systems on multiple units have recorded anomalous readings. The remediation framework classifies these as systems requiring continued surveillance. Continued surveillance is not remediation. 67 of the 149 single-shell tanks have breached structural integrity. That figure represents 45% of the single-shell inventory. The volume of liquid radioactive waste discharged through those breaches into the subsurface soil matrix beneath the tank farms is estimated at over 1 million gallons. 1 million gallons is a conservative figure. It is derived from material balance calculations comparing known input volumes against known output volumes, attributing the deficit to leakage. The actual discharge volume cannot be directly measured. The receiving environment is the Vadose zone. This is the unsaturated soil column between the tank bottoms and the water table. It is not uniformly accessible to monitoring instrumentation. The Vadose zone beneath the tank farms extends from approximately 20 meters to over 70 meters depth, depending on location across the central plateau. That column of dry, porous, basaltic sediment and interbedded silts is the first geological filter between the tank contents and the unconfined aquifer system that underlies the entire site. The migration physics of that discharged inventory are not speculative. They are documented in decades of borehole sampling, geophysical surveys, and isotope fingerprinting from the monitoring well network. The liquid waste, driven downward by gravity and capillary suction through the sediment matrix, carries a chemical and radiological signature that can be traced with precision. The high ionic strength of the waste, its extreme alkalinity with pH values routinely above 13, and its temperature at the time of discharge all affect the rate and pathway of migration. Some of the heavier radiological constituents, including cesium-137 and strontium-90, bind to clay minerals in the sediment column and retard their downward movement. This retardation is real and measurable. It is not elimination. It is delay on a time scale measured in decades against half-lives measured in decades. The retarded inventory remains in the Vadose zone. It is concentrated in Plumes. It is permanently available for remobilization by future infiltration events or subsurface water table fluctuations. The lead migration elements are those that do not bind. Technetium-99 is the primary concern in the fast-moving fraction. It is an anionic species in oxidized groundwater environments. It carries a negative charge and is repelled by the negatively charged surfaces of clay minerals rather than absorbed onto them. Its retardation factor in the sediment types present at Hanford is approximately 1. This means it moves at approximately the same velocity as the groundwater itself without significant delay. Its half-life is 211,000 years. Consider the practical implication of that combination: 0 retardation and a 250,000-year radioactive persistence. It means that Technetium-99 discharged into the Vadose zone in 1958, 1963, or 1971 is now in the groundwater. It will remain bioavailable in the regional hydrological system for geological timescales. Monitoring data from the well network confirms Technetium-99 concentrations in groundwater beneath the tank farms and downgradient toward the Columbia River. The concentrations routinely exceed drinking water standards. Iodine-129 compounds the problem in a different dimension. Its half-life is 15.7 million years. It is also anionic. It is also unretarded. It moves continuously at groundwater velocity through the subsurface. Its radioactive persistence extends far beyond any planning horizon that human institutional frameworks can meaningfully address. The concentration of iodine-129 in groundwater at Hanford is measured in micrograms per liter. The regulatory maximum contaminant level for iodine-129 in drinking water is exactly 1 microgram per liter. Massive exceedances have been documented in monitoring wells between the Central Plateau and the Columbia River. The river itself serves as the ultimate hydrological receptor for the regional groundwater system. It receives baseflow contributions from the unconfined aquifer along the Hanford Reach. The isotope budget for that baseflow contribution is not 0. It has never been 0 since the 1950s. The monitoring data documents the flux. The remediation infrastructure has not interrupted it. Tank 241 Psi 101 is a double-shell tank with an inner shell diameter of approximately 22.9 meters. At its maximum recorded inventory, it held a stored waste volume of approximately 4.3 million liters. It is the largest single radioactive waste storage vessel at the site by volume. Between 1949 and 1993, it was also the most acutely hazardous structure on the Central Plateau. This danger was entirely unrelated to its radiological content. It was driven by its chemistry. The waste matrix inside tank Psi 101 contained a mixture of high-level sludge, a semi-liquid layer, and supernatant liquid. These were chemically reducing environments rich in organic compounds and nitrate salts. The radiation field from the waste drove continuous radiolysis. This is the radiation-induced decomposition of water and organic molecules. It produced hydrogen gas, nitrous oxide, and ammonia gas as persistent byproducts. Under normal conditions, those gases would migrate upward through the liquid and escape. The waste in Psi-101 did not behave normally. The uppermost layer of the waste in Psi-101 consolidated over time into a hard, mechanically stable crust. The measured thickness was approximately 1.8 meters. That crust was dense enough and coherent enough to trap the gases generated below it. The gases accumulated in void spaces within the crust and in the sludge layer beneath it. The pressure built continuously toward concentrations that periodically exceeded the mechanical cohesion of the overlying material. The result was a catastrophic rupture. Hanford documentation describes this phenomenon as a gas rollover, a gas release event, or colloquially as a burp. The cycle repeated with a strict periodicity of approximately 100 days. The crust would rupture. The trapped gas mixture would vent rapidly into the tank headspace above. The gas mixture was highly flammable. Hydrogen and nitrous oxide in the concentrations generated by Psi-101 can form a detonable mixture. The lower flammability limit for hydrogen in air is 4% by volume. Monitoring data from the tank headspace confirmed that hydrogen concentrations during gas release events regularly exceeded that threshold. The regulatory and operational response to Psi-101's gas retention behavior developed over a period of years. During this time, the tank was classified as a watchlist tank, requiring enhanced monitoring and strict operational restriction. The administrative mitigation ultimately deployed in 1993 consisted of installing mixer pumps. These pumps were designed to continuously agitate the waste, preventing the crust from consolidating and forcing gases to escape gradually, rather than accumulating to rollover concentrations. The mixer pump installation was operationally successful in a very narrow sense. It prevented subsequent large gas release events. The gas release frequency was successfully converted from episodic and large to continuous and small. The flammability hazard in the headspace was reduced to manageable levels. The mixer pumps operated for years. They consumed continuous electrical power. They required constant maintenance. They prevented the specific failure mode of catastrophic gas release. But what the mixer pumps did not do was alter the chemistry of the waste. They did not reduce its radioactive inventory. They did not address the underlying condition that made the tank dangerous. They managed the symptom. The waste remained. The waste treatment plant, also designated the Vitrification Plant, is the primary engineered response to the tank farm inventory. Vitrification is the process of converting liquid radioactive waste into a chemically stable borosilicate glass log. This locks the radioactive constituents in a solid matrix resistant to leaching for timescales relevant to the half-lives of the waste components. The technology is proven at other sites globally. The Hanford Waste Treatment Plant was authorized to apply it at scale to the largest concentration of liquid radioactive waste in the Western Hemisphere. The project was initially scoped and contracted in the 1990s. The original cost estimate was around $4 billion. The projected operational start date was set for the early 2000s. That estimate was wrong by an order of magnitude on both the cost and the time axis. The cumulative expenditure on the waste treatment plant through the mid-2020s exceeds $40 billion. $40 billion is the sunk cost figure. It does not include projected future expenditures required to complete the facility and achieve full operational capability. The engineering history of the facility is a sequential audit of systemic design failures. Each one was identified. Each one generated a complete redesign cycle. Each redesign cycle consumed years and hundreds of millions of dollars. The primary technical challenges included the behavior of the highly alkaline, chemically complex waste streams in process piping and vessels. Specifically, the corrosion mechanisms dissolved and redistributed metals within the process stream. This created severe deposition and plugging risks in the filter and transfer systems. The pipe corrosion issue was not a secondary concern. It was identified by independent technical review boards as a fundamental limitation of the original process design. The high-level waste vitrification process stream requires the waste to be pretreated. This separates the high-activity fraction from the bulk low-activity fraction, concentrates the high-activity material, and feeds it into the melter vessels at controlled rates. The melter vessels operate at temperatures around 1100 degrees Celsius. They convert the waste and glass-forming additives into a molten glass that is poured into stainless steel canisters and cooled to a solid product. The low-activity waste stream represents the bulk volume of the tank contents by liquid fraction. It is fed to a separate melter train. Both melter trains depend entirely on the reliable operation of the pretreatment and feed delivery systems upstream of them. Those upstream systems have been a persistent source of engineering and safety concerns. The solids handling the filtration systems and the transfer pumps operating with highly corrosive slurries at elevated temperatures have all required repeated redesign iterations. The current operational projection for the start of high-level waste vitrification processing is approximately 2038. That projection represents a further deferral from previous projections. Those had themselves been deferred from earlier projections. The 2038 date is not a contractual commitment with financial penalties for failure. It is a planning assumption embedded in the current contractor baseline schedule. The gap between the 1993 gas retention mitigation on Psi-101, the 1990s vitrification contract award, and the 2038 projected start date represents a span of approximately 45 years of elapsed time. Throughout that interval, the waste inventory has been generating heat, gas, and chemical reaction products continuously. The tanks that were 4 times past their design life when this audit was constructed will be further aged when the first canister of high-level glass is poured. In January of 2026, a field incident at the waste treatment plant's emission control system resulted in the release of 7,600 gallons of anhydrous ammonia gas from process piping. Anhydrous ammonia is acutely hazardous to respiratory tissue at concentrations above 25 parts per million. It is immediately dangerous to life and health at 300 parts per million. The release triggered mandatory shelter-in-place protocols for on-site personnel in the affected area. No fatalities were recorded in publicly available incident documentation. The event was categorized as a significant incident requiring investigation and corrective action before affected systems returned to service. Each such corrective action cycle adds calendar time to the already extended operational baseline. 7,600 gallons of anhydrous ammonia released from a facility processing nuclear waste is not an isolated data point. It is a signal from a complex system operating at the edge of its design envelope. It is an infrastructure staffed and funded at levels insufficient to maintain the margin between normal operation and component failure. The surface and subsurface monitoring infrastructure at Hanford is extensive by the metrics of wells drilled, samples collected, and data points logged annually. The groundwater monitoring network includes over 1,000 monitoring wells distributed across the site and its down-gradient boundaries. Those wells log concentrations of radiological and chemical contaminants at defined sampling frequencies. This produces a dataset that documents the migration of the tank farm plume toward the Columbia River in continuous temporal resolution. The monitoring data is public record. It is published in annual groundwater reports that are accessible through the Department of Energy's public document systems. Reading those reports is an exercise in parsing the administrative distance between observation and intervention. Uranium concentrations in groundwater at monitoring locations within the Central Plateau and downgradient zones have been recorded at 51,400 micrograms per liter at individual wells. The Environmental Protection Agency's maximum contaminant level for uranium in drinking water is 30 micrograms per liter. 51,400 micrograms per liter against a 30 micrograms per liter safety ceiling is a ratio of 1,1713 to 1. That ratio is a measurement. It is not a projection. It is a documented condition in the existing groundwater system beneath a portion of the site. The monitoring well that recorded that concentration is not in the river. It is in the subsurface at a point between the source zone and the river. The gradient between that point and the river is hydraulic. The flow direction is established. The timescale for continued migration is constrained by groundwater velocity, estimates derived from aquifer hydraulic conductivity measurements. The regulatory architecture governing the Hanford Site distributes responsibility among the Department of Energy as the responsible federal agency, the Washington State Department of Ecology under the Tri-Party Agreement framework, and the Environmental Protection Agency. The Tri-Party Agreement, established in 1989, set legally enforceable milestone schedules for cleanup activities. The history of that agreement is a history of milestone renegotiation. Deadlines that could not be met were renegotiated to later deadlines. Later deadlines were renegotiated again. The legal enforceability of the milestones is real in the sense that penalties can be assessed for missed deadlines. And penalties have been assessed. The penalties do not accelerate the physics of groundwater flow or the engineering timeline of a vitrification facility. They are financial transfers within the federal budget system. The Columbia River, flowing along the eastern and northern boundaries of the Hanford Site for approximately 80 kilometers before turning toward the Pacific Ocean, is the hydrological terminus of the Hanford groundwater system. The river supports salmon populations, tribal fishing rights, municipal water supply intakes for communities downstream, and the entire ecology of the Hanford Reach. This is the last major free-flowing stretch of the river above the Columbia's mouth. The base flow contribution from the Hanford groundwater to the river carries measurable concentrations of tritium, strontium-90, technetium-99, iodine-129, and other isotopes from the tank farm Plume. The river's dilution volume is large, and in-river concentrations of most contaminants remain below regulatory action levels at current flux rates. The word current is doing significant work in that sentence. Current flux rates reflect the current state of the plume, which reflects the leakage history through approximately 83 years of tank farm operation. The plume continues to migrate. The leakage from tanks that have already breached continues to move through the Vadose zone toward the water table. The monitoring wells between the Central Plateau and the river are recording the leading edge of that migration, not the total inventory in transit. The double-shell tank system that stores the bulk of the highest activity waste fractions is not without its own degradation timeline. Stress corrosion, cracking of the inner shell steel, has been identified as a potential failure mechanism in multiple double-shell tanks. The annular space monitoring systems designed to detect inner shell leakage require regular calibration and maintenance. The unraft-level gauges used to monitor waste levels in the tanks are precision instruments operating in a highly radioactive environment. That environment actively accelerates electronic component degradation. Instrument calibration drift that goes undetected can mask slow leak rates. The administrative threshold for classifying a double-shell tank as a confirmed leaker requires documented evidence of waste transfer from the annular space monitoring system. That threshold creates a detection lag between the onset of leakage and the regulatory classification of the tank has failed. The detection lag is a structural feature of the monitoring protocol, not an anomaly. The remediation of Hanford's Vadose zone contamination separate from the tank farm inventory itself presents a set of technical challenges for which no fully demonstrated solution exists at the required scale. Technologies including in situ grouting to stabilize Vadose zone contaminant plumes, pump and treat systems to capture groundwater plumes, and permeable reactive barriers to intercept and immobilize migrating isotopes have all been deployed or piloted. Their performance data is documented. None of them eliminates the contaminant inventory. Pump and treat systems operating at the site have extracted and treated millions of gallons of contaminated groundwater, temporarily reducing contaminant concentrations in the treated aquifer zones. Rebound, the return of contaminant concentrations toward pre-treatment levels after pumping ceases, has been observed at multiple locations. The physical explanation for rebound is the existence of slow-release source terms in the Vadose zone above the water table. These terms continually resupplying the aquifer as remediated water draws down the concentration gradient. The workforce demographic at Hanford is an operational variable that does not appear in the isotope migration calculations, but directly determines the rate at which any engineering response can be executed. The site employs approximately 11,000 workers across multiple contractors operating under Department of Energy oversight. That workforce includes engineers, technicians, radiological control personnel, project managers, regulatory compliance specialists, and support staff. The institutional knowledge embedded in that workforce is not uniformly documented in retrievable form. Experienced workers retire. Contractor transitions, of which Hanford has experienced multiple over its history, routinely interrupt knowledge transfer. The half-life of institutional memory at a complex nuclear site is shorter than the half-life of Technetium-99 by many orders of magnitude. The cost projection for completing Hanford cleanup currently stands in ranges that begin at $300 billion and extend significantly higher. $300 billion is a federal commitment of a scale that competes with other national priorities across multi-decade budget cycles. The appropriation history of Hanford cleanup funding shows annual budget requests, congressional appropriations that differ from requests, continuing resolutions that defer decisions, and sequestration events that reduce actual spending. The gap between the projected cost of completing cleanup and the historical rate of annual appropriations produces a massive deficit. No current political or fiscal framework has resolved this. The waste does not wait for the budget cycle. The regulatory classification system that governs how Hanford waste is managed and disposed of is itself a source of permanent uncertainty. High-level waste is defined by its origin, meaning waste from the reprocessing of spent nuclear fuel, and carries the most stringent disposal requirements under federal regulations. Specifically, it mandates disposal in a deep geological repository. The only candidate deep geological repository for high-level waste in the United States, the Yucca Mountain facility in Nevada, has been in administrative suspension since 2010. No replacement site for a federal high-level waste repository is currently in the active licensing process. The glass canisters that the Hanford Waste Treatment Plant will eventually produce require a licensed repository for final disposal. The repository does not exist. The canisters will be stored on an interim basis at the site after production. The interim period has no defined endpoint because the endpoint depends on a federal decision that has not been made. The low-activity waste fraction, representing roughly 90% of the liquid volume in the Hanford tanks, but a much smaller fraction of the total radioactivity, is being vitrified in the low-activity waste facility, which achieved operational startup in 2023. That milestone is real. The low-activity waste facility is producing glass logs at a defined throughput rate. That rate projects a multi-decade processing campaign. The low-activity waste glass will be disposed of in a near-surface engineered facility at the Hanford Site, the Integrated Disposal Facility, pending regulatory approval. The regulatory pathway for low-activity waste gas disposal is heavily contested. Washington State has challenged the federal classification of some Hanford waste as low-activity rather than high-level. They argue that the chemical separation process used to concentrate the high-activity fraction does not meet the regulatory definition for high-level waste separation. That legal and regulatory dispute has been in process for years. Its resolution directly affects how hundreds of millions of gallons of treated waste can be legally disposed of, and therefore how fast the processing campaign can be completed. Plutonium production at Hanford operated 9 reactors along the Columbia River between 1943 and 1987. Each reactor irradiated natural and enriched uranium fuel slugs, producing plutonium-239 through neutron capture in uranium-238. The irradiated fuel was dissolved in nitric acid at the chemical separation facilities on the Central Plateau. The plutonium was chemically extracted, and the remaining liquid containing fission products, activation products, and residual actinides was transferred to the tank farms. The cumulative output of that reprocessing operation is the inventory that exists in the tanks today. The plutonium produced at Hanford, approximately 67 metric tons of weapons-grade material, was the primary fissile material in the United States nuclear arsenal for the Cold War period. The waste generated in its production is the liability that persists after the weapons program ended. The soil contamination inventory at Hanford includes over 40 million cubic meters of contaminated soil resulting from direct disposal operations conducted before tank storage became standard practice. It is the result of spills, leaks at processing facilities, the burial of solid radioactive waste in unlined trenches, and atmospheric deposition of radioactive particles. The surface soil contamination plume map covers areas distributed across the 580 square mile site. Plutonium contamination in surface soils at several locations exists at concentrations that preclude unrestricted land use in perpetuity. The regulatory framework for managing this contamination involves institutional controls, physical barriers, and monitoring. It does not involve remediation to background concentrations. The regulatory endpoint for much of the contaminated soil at Hanford is controlled land use with long-term stewardship. This means permanent human management of the land to prevent human exposure in perpetuity, defined operationally as at least 10,000 years. 10,000 years of institutional control is not a cleanup plan. It is a surrender document dressed in regulatory language. The institutions that exist today, the Department of Energy, the State of Washington, the Environmental Protection Agency, the tribal nations with treaty rights in the region, none of them existed 10,000 years ago. None of their successors can be specified. The assumption that human institutional capacity to identify, monitor, and restrict access to a 580 square mile radioactive contamination site will persist for 10,000 years is not supported by any historical precedent for institutional continuity. It is a planning assumption that fills the space where a technical solution does not exist. The Hanford Site is a closed accounting system in the following precise sense. The radioactive inventory entered the system between 1943 and 1987 through the operation of 9 plutonium production reactors. The inventory cannot leave the system faster than the decay physics of each isotope and the engineering throughput of the processing facilities allow. The decay physics are fixed. The engineering throughput is constrained by funding, by facility performance, by regulatory dispute, and by the absence of a licensed final disposal pathway. The gap between the rate of inventory reduction and the rate of inventory migration into the subsurface environment is the central operational metric of the site. That gap has been negative for every year of the site's history since active production ended. The monitoring data is the record of that negative balance. The wells document the migration. The schedule documents the deficit. The isotope inventory documents the persistence. The Columbia River flows at its current rate, regardless of the scheduled status of the waste treatment plant. The groundwater gradient between the central plateau and the river exists regardless of the budget appropriation for the fiscal year. Technetium-99 moves through the aquifer at its geochemically determined velocity regardless of the regulatory classification dispute over low-activity waste gas. Iodine-129 will be bioavailable in the regional hydrological system for 15.7 million years, regardless of the institutional control framework that governs the site. The ledger is open. The entries are accumulating. The audit continues.